Hello students, welcome to the structural analysis course. So today we'll discuss one of the important chapter of structural analysis, the analysis of continuous beam by three moment theorem. So I am Dr. Gyanendra Kumar Prusty, Assistant Professor, Department of Civil Engineering. So in today's lecture, what we'll understand, we'll see what is continuous beam, whether this beam is statically determinate or indeterminate structure. Then, what is the need of this three-moment theorem? We'll discuss about some fundamentals. And at the end of this lecture, we will discuss one of the examples. How can we solve a continuous beam using three-moment theorem? Let us enter into the chapter. So, what is statically indeterminate structure? If you ask me how to compare between statically determinate or indeterminate structure, let us see this cantilever beam. So, how many reactions are there in the cantilever beam? You see, first of all, in this cantilever beam, this end is fixed, end A, and this is the free end. And how many reactions at the fixed end? There is one vertical reactions, that is RAY, one horizontal reaction, that is RAX, and a movement, that is movement at A. So we have three unknowns. So when we are going to solve this cantilever beam, we have to find out what is RAY, what is RAX, and what is the moment developed at the fixed end. So to solve this cantilever beam or to find out these two reactions and moment, what do we need? We have to use the equilibrium conditions. How many equilibrium conditions we have? We have three equilibrium conditions. One is summation of fx is equal to 0. One is summation of fy is equal to 0 and summation of moment is equal to 0. Now we have three unknowns to find out and we have three equilibrium conditions. That means by using this equilibrium equation or equilibrium condition, we can solve this unknowns in the cantilever beam. So that's why we can call this cantilever beam as statically determinate structure. I hope you understood this. So yeah, if we consider again a simply supported beam, then you see how many reactions are there. In the simply supported beam, this end is hinge support and this end, other end is roller support. So in hinge support, one horizontal reaction is there and one vertical reaction is there. And in the roller support, one vertical reaction is there. So we have now three unknowns or three reactions to find out. And how many equilibrium conditions? We have three equilibrium conditions. So number of unknowns is equal to number of equilibrium equations. That's why this we can call this simply supported beam also determinate structure. That means we can solve this simply supported beam by using this equilibrium conditions. So what if there are more than three unknowns are available in a structure? So if there are more than three unknown reactions are there and those unknown reactions are greater than the equilibrium equations. Why? Because we have only three equilibrium equations. If more than three unknown reactions are there, then we can call it statically indeterminate structure. So for that particular structure, we need extra compatibility conditions or extra equations we need to solve the unknowns. So one of the best example of statically indeterminate structure is continuous beam or fixed beam. Let us see how a continuous beam is statically indeterminate structure. Now see, this structure is a continuous beam. So it has four supports. Let's say one vertical reaction, two, three, four. We don't know which if we can have this horizontal support, horizontal reactions also. So what is continuous beam now? A beam with more than two supports, we can call this continuous beam. The beam with more than two supports. Now, this is the end support. This is another end support. So, how many intermediate support? One and two. Two intermediate supports we have. So, this is a three-span continuous beam. You can draw also two-span continuous beam also. So, the beam has two end supports and one intermediate support. So, it is a two-span continuous beam. So, this example is a three-span continuous beam. So what happens in the continuous beam? So there are internal movements developed at the supports. The supports internal movements are developed. So because of that, we cannot solve using the statics alone. So whatever equilibrium conditions we have, I will discuss. We have three equations of equilibrium equations. By using three equations of equilibrium, we cannot solve these extra unknown reactions. That is why we need compatibility conditions or some extra equations to solve these unknowns. Okay, so next we see a fixed end support. So in the fixed end support, see this end is fixed and this end is fixed. So how many reactions are there in this end? So one vertical reaction, one horizontal reaction, and one movement. Similarly here, one vertical reaction, one horizontal reaction, one movement. We have six unknowns. So how many equilibrium conditions? Summation of fx is equal to 0, summation of fy is equal to 0, summation of movement is equal to 0. So that's why these three equilibrium conditions are not sufficient to analyze this particular structure. That is why we need some extra equations to solve this fixed beams. That's why we can call this fixed beam as statically indeterminate structure, or this continuous beam as statically indeterminate structure. So, so there are several methods to solve this statically indeterminate structure. Okay, so out of this, we can say three moment theorem is three moment three moment theorem. Three moment theorem is one of the method to solve the this statically indeterminate structure, especially this continuous beam. Okay. So similarly, there are other methods are also available. One is slope deflection method. Slope deflection method also can be used to analyze the continuous beams. There are moment distribution method also. Moment distribution method which can be used to analyze the continuous beam. So all three methods we can discuss in this particular course, structural analysis. So today we will discuss in details how to use three moment theorem to solve the continuous beams. So what is the need of three moment theorem? I hope you understand this. So first of all, why three moment theorem is required? To determine the support moments. So why three moment theorem is required? To determine the support moments. What are the extra moments are developed in the intermediate supports? We can determine that. And we can simplify the analysis of continuous beam, and we can avoid solving many simultaneous equations. Why? Because statically indeterminate structures are complex structures, so it is always difficult to analyze the statically indeterminate structure. So we need number of equations to find out the unknowns. But what is the advantage? What is the advantage of the three moment theorem? We can simplify the analysis, as well as you can avoid the simultaneous equations. If there are so many equations, you can avoid those equations, and you can simple way by using a single equation. How can we solve? How can we find out the support moments that we can see in this method? Okay. So here is, if there are three consecutive supports A, B, C, let's say here is the example, here is a simply supported and continue, this end is simply supported, both ends are simply supported, and an intermediate support is there. Let's say this is A, this is B, and this is C, and this is basically a two-span continuous beam. So in this particular continuous beam, how to solve I mean, how to find out the intermediate moments, how the moments will be developed. Let's say the end moment will be developed here, MA. Let's say another moment will be developed in the intermediate support, that is MBA, let's say. This is MAB. Let us write for the time being. This is MBC, and this is MCB. So we have the movements as developed, and the negative movements are developed at the intermediate supports. So we can find out this MB by using this equation. This equation is called three moment equations. If we have three consecutive supports A, B, and C, so let's see how to write this equation. First, we'll consider the first span, that is AB. So the moment at A is nothing but your MA into L1. L1 is nothing but your span length of length of the span 1 plus 2MB into L1 plus L2, that is your span length 1 and span length 2, plus MC into L2. MC is your moment at C and L2 is the span length 2. So see, in the left hand side, all three moments we have considered, MA, MB and MC. And with MA, the span 1 is coming. With MC, the second span is coming. And with MB, both span is there. So is equal to minus 6 into A1 x1 bar divided by L1 plus A2 x2 bar divided by L2. So this formula will apply in all types of examples, or all types of uh, continuous beams to find out the support moments. So what are the moments? MA, MB, and MC are nothing but your support moments. What is L1 and L2? Span length. What is A1 and A2 in the formula? This A1 and A2. A1 and A2 is area of the free body diagram, free bending moment diagram of the span. So that we will see how, what is free bending moment diagram and how can we draw this. Then x1 bar and x2 bar. X1 bar and x2 bar are nothing but your centroid distance from the each support. That we will see how to calculate the centroid distance. So if you ask me what is the definition of three moment theorem, so three moment theorem is nothing but this particular equation expresses the relation between the moments at three successive supports. So this particular formula you can see it expresses the relation between the moments at the three successive supports. So MA, MB and MC, and the loading of the two spans between those three supports. How many loads are there? Let's say here in this span 148 kilonewton is one point load and 12 kilonewton is one uniformly distributed load. So we have this express the relation between the movements at three successive supports and the loading of the two spans between those three supports with and without unequal settlement of the support. This is important. With and without unequal settlement. So in this particular case, let's say there is no settlement of the supports. Okay, everything is uh, perfect. There is no settlement. In some of the cases, let's say it will be given the support A is settled by 5 mm or 10 mm below B. Or sometimes it will say the support C is settled by 6 mm from B. So in that case, this particular support is settled down 5 mm as compared to B. So in that case, we have to change this equation. That also will solve one example with how can we consider the settlement at the supports, and I will solve one examples. Coming to how to find out this free bending moment diagram, how you draw this free bending moment diagram, and how to find out the centroid and the distance of the support to the centroid. Let's say consider this particular case. So this continuous beam I have divided into two parts. So this is your span 1, span 1. This is your span 2, or span AB, or span BC. So one load is, let's say, one load is applied, which is distance A from support A, and distance B from support P. So load is P. So in that case, how to find out the bending moment? We have already discussed this problem in strength of material and some of the initial lectures of the structural analysis. So first of all, you find out the support reactions. If you take the moment at A is equal to 0, then you can consider RB into the perpendicular distance. If you find this way, so your reaction at A will be P upon B, P into B by L1. So here the reaction will be P into A by L1. So when you calculate the moment at this particular point load, let's say this is C. So moment at C, if you calculate, so what is the reactions? P into A by L1. This is the force into perpendicular distance. What is the perpendicular distance? B. So it will be PA by L into B. So PAB by L1. This is the maximum bending moment, or we can call it free bending moment. And this height is also P A B by L1. This height is P A B by L1. So how to find out the area of this free bending moment diagram? So which is A1 we have used in the formula. Then A1 is nothing but the area of this triangle. Area of this triangle. So half 1 by 2 into L1 is the length into height is PAB by L1. So total is PAB by done. PAB by 2. So L1 is cancels out. So PAB by 2 is the area 1. Okay. Similarly, how to find out area 2? Looking at the second case, A, this is B and C. So in the similar way, you can find out the reactions. Okay, RB and RC. Take moment at point B is equal to 0 and find out the RB and RC. So when you find out this moment at center, similarly RC into perpendicular distance. In that way, if you calculate, so formula is WL square by 8. So the maximum height is WL square by 8. So how to find out the area? 2, second area. So area 2 is nothing but 2/3. If you draw a square here, so it is 2/3 of base into height. So 2/3 of L2 into WL square by 8. That is your area 2. So what else is needed? Another thing is to find out the centroid. You see, in this particular case, your centroid is acting here, and the distance from the centroid to the left support we can call XL, or we are writing X bar. Okay, X bar L, and this one is X R. That is centroid to the right support. So what is the formula to find out centroid to left support? XL, that is A plus L1 by 3, and this formula, that is centroid to right support, that is B plus L1 by 3. But in this case, the centroid is acting at the center, that is centroid to left support distance is XL and centroid to right support distance is XR. So XL is nothing but L2 by 2. XR is nothing but L2 by 2, the same. Now we'll enter into the examples. So here is the example with point load as well as the uniformly distributed load. So the continuous beam is here, A, B, C. Okay. So the AB length is 6 meter. AB length is 6 meter, and a point load is, that is 48 kilonewton is applied at the center. So the distance from point load to left support is 3 meter. Similarly, the BC is totally subjected to uniformly distributed load, that is 12 kilonewton per meter, and the length is 4 meter. And what other information is given in the question? The moment of inertia, that is here I, and here for the span BC is 2I is given. Okay, so we have to analyze this continuous beam using three moment theory. Before entering into the formula, to see what is the rule while analyzing the continuous beam using three moment theory. First of all, the intermediate support is always subjected to the bending moments, that is a negative bending moment. Okay, so if the end support is simply supported, then bending moment and the end support is zero. So now this end support is simply supported. So bending moment, that is MA, is zero. This support is also simply supported. So the bending moment and C is also zero. If the end is fixed support, then there will be a bending moment at the fixed support. We have to find out what is that bending moment. Okay. So these three things you have to keep in mind while solving the problems in three moment theorem. Now just write down what is the formula. Now see the previous formula what we have discussed. There is no I value, but here the I value is coming into the picture. I mean coming into the formula because in the question itself is given. It has two different type of I values. Okay, so that's why the formula is slightly modified. That is MA into L1 by I1 plus 2MB L1 by I1 plus L2 by I2 plus MC into L2 by I2 plus 6A1 X1 bar by L1 I1 plus 6A2 X2 bar by L2 I2 is equal to 0. So this formula we are going to use to solve this particular problem. Now consider span AB. So how to draw the free movement diagram of span AB? The free movement diagram is now the point load is at the center. When the point load is at the center, so which formula will apply? So PL by 4. If you don't remember this formula, you can again calculate the reactions RA and RB, take movement about A is equal to 0, find out the reaction RA and RB. Okay, so then you can calculate the movement at the center. So RA into this perpendicular distance or RB into this perpendicular distance you can calculate. So the final formula is PL by 4. So what is P? 48. What is L? 6 meter. And what is 4 is in the formula. So total we are getting 72. So this height is 72. And what is the length? 6 feet. Okay. So we need to find out the area of this free bending moment diagram. This is called free bending moment diagram. So to find out the area of the free bending moment diagram, what is the formula? Half into 1 by 2 into base into height. So 216 we got the area 2. And what is x1? X1, what I told you in x1, x1 is nothing but centroid to left support. This is your x1 or xn. So x1 is 3 meter central to left. Similarly, in case of span BC, how to find out the free bending moment diagram? So the formula is WL square by 8. So total we are getting 24 kilonewton meter. And what is the area? So this should be area 2. So area 2 is nothing but 2/3 of base into height. It is 64. We are getting the area 2. And x2 is your CG2. This is your x1. This is your x2. Or you can call it xl. You can call it xr. Okay. So the x2 or xr is equal to 2 meter in this case. Correct? Next, we'll see, we'll put all the values in the formula. So as I told you before, so if the end condition is simply supported, if the end condition is simply supported, then what will be the moment? The moment at A will be 0. And what will the moment? Moment at C will be 0. That's why in this particular case, we have considered MA and MC is equal to 0. Then let us put these values in the equation. So MA into L1 by I1. So the whole segment will be 0. Then 2 MB, 2 MB, 2 MB into L1 is nothing but 6 meter. So 6 divided by I1 is I is given in the question. I1 is I. Plus L2 is 4 meter divided by I2 is 2I plus MC is 0. So this section is 0 plus 6 A1. A1 we have calculated before, that is 216. Then X1 bar is we have calculated 3 divided by N1 into I1, that is I, plus 6 area 2 is 64 we have calculated. Then X2 bar is 2 divided by 4, that is your L2 into 2y is your I2 is equal to 0. If you solve this particular equation, we are getting into 2 MB into 8 plus 648 plus 96 is equal to 0. So from here we can calculate MB is equal to minus 46.5 kilonewton meter. So MB is nothing but your intermediate support. As I told you before, your intermediate support is always negative moment. So it is minus 46.5 kilonewton meter we have calculated from these equations. Now let us draw the bending moment diagram. So one thing you remember while drawing the bending moment diagram, first we have to draw the free bending moment diagram, which we already know the formulas and we have already drawn it before. Then we'll draw the end moment diagram, end bending moment diagram, then which we have already calculated this intermediate, the bending moment at the intermediate support. And after that, what we'll do, we'll plot these two diagrams, this free bending moment diagram and end moment diagram. So we'll superimpose these two diagrams and we'll draw the final bending moment diagram. So let us draw this free bending moment diagram. We have already calculated what is the height of the first bending moment diagram, that is 72. Second is parabolic, that is 24. This is all about the free bending moment diagram. If you draw the end moment diagram, so MA and MC is 0 and MB is minus 46.5. So we can draw the baseline. MA is 0, MC is 0 and MB is minus 46.5. So we can keep it negative. Or the opposite also you can draw, like we have drawn it here. So baseline of 42 to 46, and I can give the symbol negative. Okay, that is the negative bending moment. So how to draw the final bending moment diagram? The final bending moment diagram is we have to superimpose these two diagrams. So you see, first we have drawn the free bending moment diagram. First we have drawn the free bending moment diagram. Okay, this is 72. This is 24. Then here it is 0. Here is 46. And here it is 0. It is also 46.5. So we can draw this, superimpose on the free bending moment. We can superimpose this bending moment diagram with the free bending moment diagram. So whatever initially it was positive, this is negative, this is positive. So this is your final bending moment. The final bending moment diagram. And one more thing also, once you calculated this end moments or intermediate moments, after that again further we can calculate the reactions RA, RB, RC and we can calculate the shear force also. So that's why this is the complete analysis of the statically indeterminate structure. Initially, you use the three moment theorem to solve the calculate the intermediate bending moments. After that, we can go for the reaction calculation and shear force calculations. I hope you understood this particular problem, how to solve a two-span continuous beam which is having one point load at the center and an UDL in the other span, and how can we calculate the intermediate moments at B or intermediate supports. So, summary of the lecture is, what is the purpose of this lecture? What is the purpose of this three moment theorem? The three moment theorem, which is also called as Clapeyron's theorem. This is important. Sometimes it is asking on the name of this scientist, that is Clapeyron's theorem. So the three moment theorem, it relates the bending moment at three consecutive supports of a continuous beam, enabling analysis of statically indeterminate beams. What is the use of this three moment theorem? It forms one equation. That is important. That is the benefit of this method. So it forms only one equation which is connecting adjacent spans and allowing unknown support moments to be calculated systematically when the span length, load, and flexural rigidity are known. So in that situation, we can use three moment equations to solve this particular problem in a simpler way. I hope you understood this problem. So next class, we will solve similar examples by using the three moment theorem. Thank you.